It's isometric, okay? This star algebra morphism is even isometric. Star algebra means, I mean, L infinity comes with its star operation, which is just taking the conjugation. And in B of H, of course, it's the star of, I mean, the adjoint, taking adjoints. So, okay, and it's multiplicative and all that. Now, the image of this algebra, again, this is B of L2, satisfies that its centralizer is A itself. Now, A is abelian, so what this says is that A actually in here is maximal abelian. Okay, or what I will abbreviate as a massa in B of L2. Okay, indeed, so how do you prove that? This is instructive, so let's show it. So if t is in A prime, then I'm taking this vector xi, which is t of 1, the image of 1. This is the vector 1, okay, in L2. The constant function equals to 1. This will be an L2, okay? And I denote by lambda of xi this multiplication operator by xi on L2, which of course would land me a bit away perhaps from L2 in L1 because it's a product of two L2 functions. And by Cauchy-Schwarz, this map is bounded from here, from this L2 norm to L1 by the norm of xi. So it's a bounded operator, linear operator from L2 to L1. But t is also from L2 to L2, it's therefore into L1, is also bounded as an operator into L1. So you have these two operators, and the fact that you have all this commutative situation, I mean that t commutes t commutes with all the elements in all the operators in lambda of x for x in L infinity, shows immediately that lambda of psi and t coincide on L infinity viewed as a subspace of L2, okay? And that's one of my preferred exercises for the qualifying exam at UCLA, to tell you the truth. So, okay, here is another exercise. So, therefore, lambda of psi is equal to t on all L2, and that forces psi to be in L infinity. That's the second part of this exercise, qualifying exam. Well, this shows that A is a von Neumann algebra because it's a commutant of something, okay? So, now I'll construct another example, our hyperfinite one factor. So first of all, what is a factor? This is we'll call a factor so sometimes you call it a von Neumann factor, or we'll just call it a factor because of our context is, the framework is von Neumann algebra, so that's understood that it's a von Neumann factor. Is a von Neumann algebra whose center, so that's the set of elements in M that commute with all elements in M. So I wrote here using the M prime the prime notation, M prime intersected M, is trivial. By that I mean that it's just the scalar multiples of 1. So we'll start like this. We take the 2 by 2 matrix algebra and take the infinite algebraic infinite tensor product. So these are just, tensors, so infinite tensor, but where you only take elements that have 1, 1, 1 from a certain point on, right? So it's finitely supported that way. And you can, of course, obviously also view this as like an increasing sequence of the 2 to the n by 2 to the n algebras, which is just the tensor product only from 1 up to n, with these embeddings, which for matrices look like this. Right? So that's how you go from from 2 to the n to 2 to the n plus 1. And we'll endow R0 with the norm. Now, each x is in some 2 to the n matrix algebra, and you just take its operator norm there. And obviously these are isometric, so if you go further, if you pick a larger M where X lies, it will be the same operator norm, okay? So this, therefore, you have a well-defined norm, and it satisfies this so-called operator norm axiom, which is, of course, it's a Banach algebra norm, that's obvious, and clearly also the norm of the adjoint of X star is equal to the norm of X. By the way, I didn't mention it, but you know, our star operation, you know, it's the adjointness when you act on the Hilbert space, but in general, when I'm saying a star operation, that means, you know, an operation that's anti-linear. So, okay, on the one hand, and on the other hand, you have that it inverts the order of operation, and that also the star star is equal to X. So it's so when I'm just saying a star operation, I mean an operation like that, anti-linear on the one hand and satisfying these two properties. Okay, and also R0 comes with a functional, okay, which is the normalized trace. So that's, I'll denote it generically by tau of X. That's the trace, the usual trace, okay, the sum of the diagonals of the diagonal entries divided by 2 to the n when X is in the 2 to the n by 2 to the n matrix algebra. Now this is again well defined, obviously, right? So that because of normalization, the trace, normalized trace doesn't depend where you take it, okay? And it's positive functional, so positive elements are the elements of the form X star X, and obviously this is, you know, being just the restriction to the 2 to the n matrices, we know it's positive and satisfies the tratiality axiom. Trace of xy is trace of yx for all xy. And because of being normalized at each step, the trace of 1 is 1. So this gives you something that's everywhere defined. And by the way, something functional that's positive with trace of 1 equals 1, it's called a state. And because of the tratiality, this is a trace state. And now with that, we define a Hilbert space. Let's denote it L2 of R0. We should mention here tau, which is like a sort of integral, okay, you know, on this function space, which is R0, kind of, except that this is non-commutative, okay, defined. So we define L2 of R0 to be the completion of R0 in the Hilbert norm given by the trace in this manner, okay? Okay. So you should keep in mind, obviously, the way one also constructs, I mean, the way you complete L infinity to get L2, but even more so because this is like, you know, it's this kind of dyadic thing. So instead of that, think of the algebra of all step functions which are dyadic, meaning that, you know, the breakpoints are at k over 2 to the n for some k and some 2 to the n, right? So what I call the dyadic step functions, okay? So this would be like you get the completion of that in the L2 norm, obviously gives you all L2 of the probability space X, and it's in that spirit you get this Hilbert space here. And just to keep track of R0, when you view it here, rather than as the initial algebra, I'll put a hat on those elements that, you know, I view as elements in this L2 space. And for each x in R0, now we define lambda of x like we did before, the operator on this Hilbert space of left multiplication. So this is for all y in R0. I should have put, yeah, actually the hat is here. So, and now, this map, which takes you from R0 to lambda of x in B of L2, is clearly a star algebra morphism. Just think of the way we constructed. This is an exercise, but it's very easy. It's a star algebra morphism. It's isometric, okay? It's clear because, you know, you just take this for x's in 2 to the n by 2 to the n matrices where it's, this whole thing is obvious, and this is clearly just, you know, locally it's just that, okay? And you recover the trace on R0 as a vector state, as a vector functional, which is kind of important. And one similarly defines rho of x to be, now here it matters, unlike before where the space was the algebra, function algebra, L infinity of x was commutative here, and it didn't matter that we multiplied left or right. Here it matters, we have also a right multiplication operator, after all, why to just take the left, by x on L2 of R0, and clearly the two commute, okay? Now, I mean, of course, when you multiply from the right, the order will change, so it will be more like a star algebra morphism, but not from R0 into this B of L2, but rather of R0 opposite, where x times y in this R0 opposite is y times x in R, okay? So, where you change, because it comes from the right, so you will otherwise not have that, you know, it's a okay, one can easily see that this for Neumann algebra, which is the SO closure of the image, or VO closure, is a factor. That's an exercise. That's, again, you know, because of this, the way this inductive limit, it's very easy exercise, actually. And one can alternatively define it as the commutant of rho of R0. That's another exercise. And you know, actually, as it happens, it's very similar to the proof that A, in the previous proof, that A was maximal abelian, that anything commuting with it was, you know, a multiplication operator with something in L infinity. It's really identical. So it's a reasonable exercise, okay? It's just playing with this lambda and rho in a sort of smart way. Well, this is the hyperfinite II1 factor. Now there is this word which suddenly pops out, this II1, this index, so that terminology will be justified soon. So we will, you know, so just, you can just call it the hyperfinite factor, which actually would be probably very correct. I mean, yeah. However, yeah, you will see there is a nuance, because we should say infinite dimensional hyperfinite factor or something. So. Now, yet another way to define R is, like I said before, also with L infinity of x. Actually, I didn't say it that way, but it was sort of implicit, as the completion of R0 as follows. You take the topology of convergence in norm 2, but on bounded sequences, okay? It's like, you take the dyadic step functions on a probability, on 0, 1, okay? On 0, 1, so by the way, I mean, even before when I was saying, you know, not on any x, when I'm saying dyadic partitions, dyadic step functions, that's when I take the probability space 0, 1, okay, and the dyadic, we use that terminology. Okay, so you take the step functions with jumps at k over 2 to the n, the dyadic step functions, and that forms a star algebra, obviously. Well, its closure in this manner, okay, is L infinity of x, right? okay, as we know, from classic theorems. So you can, that really tells you in a way that, this hyperfinite factor, because of all the way, the 2 to the n by 2 to the n matrices, which you can look at as non-commutative dyadic step functions, right? 2 to the n, and the way we embed them this way is very similar. Actually, it's, for the 0-1 interval, it's like splitting, halving consecutively, right? Into 2 and so on, okay, each interval. So the way you get this way, all the dyadic partitions and step functions, corresponding step functions. So, and in fact, of course, if you take D0, I denote the diagonal in R0, so just the diagonal, you keep track of that in all this limiting process that gave us R0. Okay, that's nothing but this algebra of dyadic step functions. Okay, and the closure with respect to this norm is just the closure I said before in the L2 norm on L2 of 0-1. So the closure, the completion that we operate on R0 to get R, the effect of that when we restrict to this D0, it gives us L infinity of 0-1, okay, which sits like a sort of diagonal in R, in our hyperfinite one factor, okay? So hyperfinite one factor is like a non-commutative interval, okay? It's the quantum 0-1, okay? So it's a fascinating subject because, as we will see, it has lots of remarkable properties. And I just want to point out that there is this remarkable sequence of elements in all this construction, which simply says this, that I'm taking this diagonal that I kept. So this is the first, the diagonal of 2 by 2 matrices, right? But usually, of course, you put it this way, the unit interval, you put it here. So it's, it's just multiples of this projection plus multiples of this projection. This is your splitting of 0-1 into 2, okay, and then and so on, right? You split in 2 and so on and so on. And if in that writing with the as infinite tensor product, if I denote the matrix units by I used I, okay. EI KL, with the lower indices, just 1 and 2 possibilities. So what I emphasized here with these notations, you will see later the reason I'm doing that, is this. So I'm writing Pn are these projections, so this one. Then I split the rest in 2. I'm taking this one. Then I'm splitting the rest in 2. This is P3, and so on. And each time I also keep track of, first here it's V1, is the partial isometry that gives me the equivalence between P1 and 1 minus P1. This is E1, 1, 2, this is V1, and Vn is, so each time, so V2 is the one that gives me the equivalence between these two. So 1 minus P1 minus P2, okay, and so on, okay. So this is P3, etc. Anyway, so we have these partial isometries and projections which satisfy these these properties. Okay, so you see P2 is equivalent with 1 minus P1 minus P2, which is this, and so on. Now, I insist on that because this is what we will do when proving this theorem, okay? So I'll basically, what I want to show is this remarkable theorem from you see, all this subject, as I said, was initiated by von Neumann in 1929 when he proved the theorem. He actually wrote several papers in the 20s, 30s, the spectral the functional calculus, all the things that were developing at that time from quantum mechanics, motivated by quantum mechanics and representation theory. In any case, at some point he started to work with his postdoc, Fred Marais, and that started that collaboration in 1936, and then there was a sequence of papers called rings of operators, and this, I guess, it's in construction of the traces from rings of operators 2, I think, from 1939, I believe. Okay, and which is this theorem, which gives you several equivalent conditions for a von Neumann factor to have a trace like the hyperfinite factor that we had as an example before. And after all, also, I mean, yeah, and biometrics obviously to start with. The reason this theorem is remarkable is because of the equivalence of these two. The others are just, kind of refinements of this. But so it says that a von Neumann algebra, a von Neumann factor, satisfies this so-called finiteness axiom, which says that a projection, for two projections I did not introduce, so I use this notation for the projections in M, and you write that P is equivalent to Q if there exists a partial isometry in M such that on the one, it has the source P and the range Q. Okay, you sometimes also write like that it's an equivalence given by such a V. Okay, and also you have P less than Q if you have that there exists V as before such that V, so again is the P okay, and this says that you cannot, that if you have a projection that's equivalent to 1, then P must be equal to 1. So in other words, it's like requiring this axiom. If V star V is equal to 1, then V star must also be equal to 1. Okay, this is what this says. So it's finiteness because this is like for sets, you can only have a set is equivalent to a strictly smaller subset only if the set is infinite, if and only if the set is infinite. So finiteness is, by the fact that it's, doesn't mean that it's finite dimensional, but it's that, it's finite in the von Neumann algebra context means this thing, which is, because, of course, motivated by finite d-many, in set theory, the most silly kind of, observation, right, with, 6th, 7th grade in school of that level of set theory, okay? So any isometry says it's necessarily a unitary element. Now, that is a pretty abstract, you could say very algebraic in any case condition, axiom. And suddenly, the second condition, which is supposedly equivalent to this, is that M has a trace state that is a functional on M that's positive, okay? Trace of 1 is, at 1 it takes value 1, and it has the partiality property, okay? And then, you know, you have that also, in fact, it's equivalent to having a trace that's completely additive, and so that's not completely additive, exactly like for a measure. So, you know, okay, so the trace of sum of mutually orthogonal projection is the sum of the values at pi, and or normal, also equivalent to this, which is a bit stronger than that. Of course, this implies that that the sup, you know, goes out. So the limit, SO limit for an increasing sequence comes out of the, you know, trace, commutes with that. So it's continuous in that sense. Okay, so for Neumann factor is finite if and only if it is Trashian. That's the terminology we'll give to all this. And as a matter of fact, let me point out right away that such a factor, if you know you have this property, then you can prove it has a unique trace state, which is automatically normal and faithful. And in fact, this is how you practically can obtain it, as you take the norm closure, this closure here of the convex combination of these averagings by unitary elements, or by odd u with u unitaries in M. Okay, you take the convex closure, and that the norm closure intersects the center, actually the scalar multiples of 1, and exactly at 1 point, and that's the trace. Okay. This part is Dixmier's theorem from the 50s, 1950s, okay? So only up to here is. So incidentally, I cannot stop myself from telling you that, so it's a very nice proof, which I wanted to sketch. I'll do that before, until, you know, we break, perhaps, you know, in the following 10 minutes, sketching the proof. And so according to Dick Addison, who unfortunately passed away in August last year, was you know, one of the so-called founding fathers of this subject of operator algebra, and he says that, I mean, he was also a postdoc for Neumann at Princeton. After he finished his degree at his PhD in Chicago, he went to Princeton and was a postdoc of von Neumann. And so he says that von Neumann told him that the proof that you will see is Fred Marais. So, you know, one should not think that Marais didn't have, you know, probably had a significant contribution to this, you know, joint work. I mean, his name should not be kind of, you know, viewed as absolutely, you know, kind of, was a very good mathematician. So here is the proof. I mean, so one more time, you see, the idea is how to construct this state out of nothing. I mean, basically you have this. And what I will try also to emphasize is that, in a way, you know, this splitting of the unit interval dyadic consecutively with the partial isometries, so that's actually what we will construct. Okay, so some sequence of projections like this with the partial isometries, which give the equivalence, and we'll measure any other projection with this. So we'll view this as, you know, like a set of unit measures, like you have a meter, decimeters or something, centimeters, millimeters, and so on. So this is all, except that we'll do it diagonally. And so we'll measure each thing, you know, with this kind of, you know, initial starting unit measures, okay? And so by doing that, obviously, because of the observation I made on the previous page, is like at the same time constructing a copy of the hyperfinite II1 factor inside, you know, any such finite factor. By the way, actually we have to exclude right away, you know, one case. So let's do that. So notice that if a von Neumann factor M has a minimal projection, this is a minimal projection, then M is necessarily of this form. It's the algebra of all bounded operators on some Hilbert space. So, and if it is like that, then you know you can have a trace state, I should have said here, okay, if and only if the space is finite, the Hilbert space is finite dimensional. Okay, so, and it's also equivalent to M being finite. So, okay, so one more time. First of all, all this is an exercise, okay? First part, but also the second, which is very easy, okay? So on B of H, if H is infinite dimensional, you cannot have a trace state. We have a trace, but it's you know, not everywhere defined, okay? Its trace of 1 is infinite. Okay, so we can exclude that. From now on, we will assume that our finite von Neumann algebra has no minimal projections. That's something that one often calls diffuse von Neumann algebra. Okay, so let's start. Okay, so the first lemma, I mean, it's a more substantial one, is that if M is a finite, well, let's take it a factor, okay, and if P and Q are projections that are equivalent, okay, then the complements are equivalent, okay, and also that if M is finite, then when you cut a corner of it, all corners, like in the sense we said before, will be also finite, meaning, one more time, that if Q is a projection less than, that amounts to this. If you have a projection less than another and they are equivalent, then they must be equal, okay? So you have that, okay? Well, this is easy using the comparison theorem. Comparison theorem says the following. Okay, it says that if M is a factor, because that's what we are, yeah, and I take two projections, then either you have that P is less than Q in that sense, or Q is less than P, okay? So, and that you prove kind of easily, okay? It's an exercise. These are very basic things. In general, you will have that if you don't take this, then you have that here there exists a projection in the center of M, a projection such that you have this under under Z, and under 1 minus Z you have the other. Okay? Since you have no center projections other than 1, non-zero, in the factor case, that amounts to what I said before, 4 factors. Okay? So it's an exercise. The third lemma is that if you have a von Neumann factor, I don't even need finiteness property here, just that it has no atom, so it's not a B of H. And you take a projection, well, I guess this was redundant because, yeah, this was redundant. This is because I had another version. Sorry about that. Then you take a projection that's non-zero, then you can split it in two. And here is the proof. It's by a maximality argument. You just take, you know, projections that are equivalent in under P mutually orthogonal, and so all on the left are mutually orthogonal, all on the right, but also between them, and they are all under P, and you know, so obviously, with respect to inclusion, this is inductively ordered, so you take a maximal element, and if you have a piece that's, you know, if it doesn't sum up to 1, if it does sum up to 1, you prove this, obviously. But if it doesn't, since you have no atoms, this dimension is infinite, so you can again find two projections that are equivalent under. And you just, you know, contradicted the maximality. And now this is crucial, okay? And it's trivial by this lemma that you can, after you split it once in two, okay, let's now assume is a factor with no minimal projections. Actually, it's again, you know, I only need that it has no minimal projections, because that's the only thing that we needed here. Then you have a sequence of mutually orthogonal projections such that it's exactly like I done here. Okay, so you can split in two, then the next one in two with these two equivalent, right? So which amounts to 1 minus the first two is equivalent to this, and so on. Okay, so you can split consecutively in two. I'm not splitting everything, you know, it's only on this side. So I leave P1, and then 1 minus P1, again I split in two, okay? So we don't need to split everything. We don't need all the dyadic part, just, you know. Okay, so you just apply S3, lemmas 3 recursively. So now, the fun thing is that if you have the finiteness axiom, it's only now that we'll use it, is that, you know, it helps you even describe the topology. So you already have your topology here because of this sort of unit measure. So what this says is that if n is a finite factor, you have a sequence Pn like before. If you have a projection that's less than all of them, then it must be 0. Now, equivalently, if P is different from 0, then there exists an n such that Pn is less than P. Okay? Moreover, if n is the first integer such that, you know, Pn is less than, is majorized, that's the word one uses for this symbol, majorized. P majorizes Pn. And Pn prime less than P is the one that's equivalent to Pn, okay? Then P minus this Pn prime must be less than Pn. I mean, majorized by Pn. And here is why this implies in a way, the topology, the SO convergence, at least for projections. So if Qn is an increasing sequence and Qn is less than Q, with Q minus Qn is less than Pn for all n, then Qn converges to Q. Okay? And also in particular, you have the sum of Pn is equal to 1. Now I would really like that you do this basically as an exercise. So the only crucial thing is, where am I using the finiteness? It's here. So if you have that P is equivalent to Pn prime under Pn for all n, I can find that, then you have mutually orthogonal, infinitely mutually orthogonal projections, namely this Pn prime. They are under Pn, so they are mutually orthogonal, and they are all mutually equivalent, right, with P. So if you sum them up, you get a projection. If you sum up just the odd ones, you have another projection that these two are equivalent, right? This is set theory, right? So this P0 is less than and different from P, and it's equivalent to P, contradicting the finiteness. The rest is really a completely trivial exercise. Okay. So this is very elementary. Everything is actually, by the way, I forgot to say, the proof is very nice, but it's extremely elementary. Of course, you have nothing at hand, you know, it's just some axiom. So it's very... Okay, so because of this, if you have a finite factor without atoms and P is a projection, then you can find a unique infinite sequence such that P increasing sequence, strictly increasing, such that P decomposes as a sum of Pn prime and K, for some p prime and k that are equivalent with p and k. So it's exactly what I was saying. You know, you come with your centimeters and start measuring. You know, how many, you know, you see what I mean, except that it's dyadic, right? So this is trivial. You just apply part A of the lemma 5. It's really a very trivial exercise. By the way, you notice that I made a choice. It's like writing any real number in dyadic form, but with infinite sequences, which are not zero from a certain point on. So rather than that, you choose to have 1, 1, 1. So for instance, the projection 1 decomposes as P1 plus P2 plus P3, so you decompose it that way, okay? Or say even P1. P1, you don't decompose it as P1. You decompose it as a sum of projections projections that are equivalent to P. So it's some, you see what I mean, right? So you write it as, so 0.1, you choose to write it as 0.01111. That's your write-up for 0.1. This is like P1 in base 2. Okay. So now, if M is a finite factor without us, then we let dim be this map from the projections of M into 0, 1, defined by the dimension of 0 is 0, and the dimension of P is this sum, where this N1 and 2 are given by lemma 4, because remember, that was unique, okay? So this is your trace, okay? It's a dimension factor. Well, it's clear that it satisfies these properties. Actually, it's an exercise, it's a bit tedious, but it's kind of really feasible, okay? So it satisfies this property. The dimension of Pn is 2 to the minus n, although you saw how we constructed, I mean, it's this choice, you know, for Pn. So, but it does sum, it's like writing 2 to the minus n as the sum of 2 to the minus n minus 1 plus 2 to the n minus 2, and so on, right? And you have this, that P is equivalent to 2 if and only if, I guess here, I should have said is equal. Yeah, I'm sorry about that. So this is the dimension, they are equivalent if and only if they have the same dimension. And it's completely additive. It's actually here that you need to, here, all this A and B, of course, are trivial. It's C that, but even C, it's very easy, okay? So it's an exercise. Now, this comes the more serious thing, and I was planning to finish this in the first hour. So the Radon-Nikodym trick, this is what this says. Let me tell you, and then, you know, I'll basically probably fly through it because I still wanted to have this done. Well, actually not. Let's state it, and then we do it after the break. So I take two functions now from the projections on M2 with values in ZR with just the property that they are completely additive, okay? And phi different from 0. And I take an epsilon. Well, then I claim that there exists a projection in M of dimension 2 to the minus n and some theta such that phi and psi, okay, after scaling phi with some theta, so, you know, inflating or diminishing it with this theta, I squeeze psi between this multiple of phi, you know, modulo some epsilon, okay, for all projections under P and P. Now, why is this the Radon-Nikodym trick? So we, out of nothing, we have to come up with this lemma just because of the, basically it's lemma 5, you know, that lemma 5 that allows us to measure everything with this sequence of projections Pn, what I call the unit measures, right? the meter, decimeter, centimeter, etc. Okay, and so what this says is this. So say you have a trace. Okay, we imagine it this way, so that we have a trace after the fact, right? And so, and that, you know, we somehow know that both phi and psi are radon-Nikodym derivatives of that trace. So by that I mean that it's that trace times some function, okay? We can even in a way, you know, just think that m is abelian, you know, for complete clarity of what we are doing here. And then you have like this. You have the two functions which give you the phi and psi, okay, the radon-Nikodym derivatives of your initial thing. And what I'm trying to do is exactly this, you know, that I take some piece on which, you know, these are basically constant and one is the multiple of the other. After scaling by theta, I make them, you know, up to 1 over epsilon, 1 plus epsilon, you know, I squeeze this between multiples. Okay, so it's very intuitive. Okay, it's not a big deal, except that we have to do this just from, you know, something, it's almost an exercise in logic because you have so little axioms. You have an object that's, you know, very kind of abstract with very few properties, and out of that you have to come up with this. So it's very little we can do, and indeed, you know, so I'll denote by F all projections that are equivalent with one of those from your unit measures, okay? From that set Pn. I call it just the unit measures. In what I, yeah, I know the name in French, but I don't, I was not able with my students to ever come with a good translation in English. Lettre étalon. That you have. Okay. So note first, we may assume phi faithful. That's very easy. So this is the one that's here, you know, that squeezes the thing. So why? Because you take a maximal family. Incidentally, it's phi that's different from 0. So for sure, you will have. I take a maximal family of mutually orthogonal projections. That for which phi is 0, okay? And I take their sum, okay? On the complement, I claim that under the F, which is the complement, the phi is faithful. That's obvious because of the maximality, okay? So I can assume it's maximal. You see how strong it is, the property of complete additivity. Huh? So, and by the way, I can diminish it to be also in this family, okay, so comparable with my meters, centimeters, etc. So therefore, I can, you know, so proving basically what this shows is that proving the lemma for M is absolutely equivalent to showing it for FMM, because here, splitting here into 2D pieces, it's like splitting here, so, okay. Okay, so now if psi 0, this is the one that we squeeze, you just take theta 0. So it's nothing, you know, if this is 0, the top, then of course there is nothing really to prove. So we can assume it's non-zero, and now I renormalize them so that phi of 1 is 1 and psi of 1 is 1, because of course, because of theta, it doesn't matter. So we show that this implies number 1 here. There exists a G in F such that for all G0 in F that's under G, we have that phi is less than psi, okay? Okay. So, well, this is plausible if you think of this picture. This should happen, definitely. Anyway, for if not, then you have that for any G in F, there exists a G0 less than it, such that phi is larger than psi. you take a maximal family of mutually orthogonal then with this property phi of gi is larger than psi of gi, and if 1 minus the sum of this maximal family is not zero, then you take a g in f less than this, conform lemma 5, and apply 2, so this contradiction has to get a g0 in f under it that's larger than this, and of course it contradicts the maximality. Thus, we must have that the sum is 1. So what you get is 1 is equal to phi of gi, this is because phi is completely additive, okay? This is larger than this, I'm sorry, it's here that you use the complete additivity, which is larger than this, which is psi of this, which is 1, and it's a contradiction. So 1 holds true, okay? So I bounded that way. You know what? Let's just stop after this. I define theta to be the supremum of theta prime that satisfies this. Okay, so I am pushing this. This is what I'm doing. I'm pushing this to the maximum so that it's under. Okay, and that's what I'm doing. And then we have that it's larger than 1 and finite, and it satisfies this property, that theta, after inflating with this theta, will give us that theta 5 is less. Moreover, because of the definition, you see, this is the soup. So if I inflate it by, or rather, or how do you say, if okay, there will exist a g0 less than g such that theta phi of g0 is larger than 1 minus epsilon psi of g0. Or else, you know, you take a theta that's larger, right, by 1 plus epsilon. So we repeat now the argument for psi and theta times 1 plus epsilon phi on this to prove this. So basically now I'm doing it from the other side. Okay, so this is the, or if you prefer, it's, you know, putting this under. So it's exactly the same reasoning, and okay, and yes, so you get the other side. Okay, it's exactly the same way we got it, you know, pushing it up. Now it's from the other side, and you get it because of the you get this for the, by the way, only for the projections in F, which are under, you know, we found the projections, so that for all projections in F under that, we have the desired inequality, and by complete additivity and lemma, I think actually was 5, we are done because any projection is a sum of those, or maybe 6, I don't know. Okay, so this is the Radon-Nikodym, and this is crucial, okay, which, by the way, will be this. So this is what we'll do after the break. We'll apply this to one function will be dim. You remember that these are not linear necessarily. We didn't use linearity in any way, just complete additivity, okay? So it's linear on projections, mutually orthogonal in that sense. So it goes some, and complete additivity, though that was crucial. But what we are now using, that it's a von Neumann algebra, so M is in B of H and is BO SO closed, okay? We didn't use at all. And one of the reasons I wanted to do this proof is because it's a famous problem, the AW star problem, which you know, up to a certain point, you know, this would prove that conjecture. Unfortunately, from a certain point on, the argument breaks because, yeah. Okay, we'll see that after the break, 5 minutes. Nikodym trick, the Radon-Nikodym lemma, to one function being the dimension function, psi, and phi being a vector state on S. So I'm representing M on a Hilbert space, so it's only now we are doing that, okay? And there I'm taking this, the phi to be that one. So I'm squeezing psi, you know, I'm between some inflation or deflation of phi, right? So this, you remember. So that implies this, that for any epsilon there exists a projection which I can take from that state space F, so dimension of the projection 2 to the minus n for some n, and a vector state phi 0 on PMP, okay, such that for any q in a projection in PMP, we have that dim is squeezed between these multiples of phi 0. Yeah, I guess here it's not quite right, because this is phi 0 if I take it to be a state on PMP, right? I should have renormalized, right? Because you see, it's not right. It's the dimension is squeezed, but I have to it's the dimension of Q over the dimension of P. It should have been normalized here. Sorry about that. You see, because I'm saying that it's a state on PMP. Well, I probably, the other easy way is not to require to be a vector functional, okay? So let's do it, instead of state, a vector functional on phi 0 on PMP, okay? So actually, phi 0 of Q to be 1 over 2 to the n. Okay. So that's of course trivial, because I'm, just applying that, for the two of them, and that's nothing. This is the reason we wanted that. Now from this, what's the point here? What am I trying to do? I have the dimension function, okay, which is defined only on projections. And I want to show that there is a state behind, a trace behind, okay, that there is a trace which on projection is equal to these dimension functions. Now you can clearly extend the dimension function to positive elements. We will see that by writing any positive element as its dyadic decomposition. If you have a positive operator, I hope all of you know this trick. You can decompose it uniquely like this. If you have an operator, so it's in B of H, but also in a von Neumann algebra, you write it in this manner. For some projections En. Okay, this is called the dyadic decomposition of X. And this, you have a unique way of doing that, okay, by spectral calculus. Okay, and so you take the biggest, well, you do this as an exercise, but it's kind of, okay, so we can do that, and from M plus you extend it to the real, to the self-adjoint part of M by taking the positive minus the negative, and then you complexify. But of course that function that extends dim in this manner will not necessarily be linear. So the reason I need the Radon-Nikodym trick is to show the linearity of M, okay, of the extension of the dimension function, okay? That's what we are trying now to do. So on a small piece, I squeezed dim between two things which I know are linear. Okay, so it's approximately linear, which obviously implies the epsilon being arbitrary, some linearity, but is not global, with the same epsilon. So this is how you globalize that. Okay, so with P phi 0 as in here, I'm taking partial isometries, which take this projection P, which has dimension 2 to the n, 1 over 2 to the n, and put it 2 to the n times, equivalently to fill up the identity. Okay, that's what it means to have dimension 1 over 2 to the n, if you remember. And with this partial isometries, I define this function, this functional phi of x to be phi 0, okay, of, so I take any x in M and I cut the you know, this, by the right supports of the VI. So VI have left support all equal to P, okay, and right supports filling up the identity. So I'm cutting x's, you know, this is, x is somewhere here, okay, and here is, these are these projections with the corresponding partial isometries that take you. So I'm cutting the x here, this corner, this piece. So this is I did not make a notation for the corresponding projections VI star VI, but this is VI star VI. So from here, okay, x compressed by this and VI star here, okay, and bring it on the first spot, right, on P. In this way, and I sum up. Okay, so this is the obvious way in which you should define phi to be defined on all M once you know it on this corner. So this way, everything is reduced to calculating things in here. This is P, which is V1, star V1, right? Okay, so here is P and P. So I brought everything here and calculated there with phi 0. So then phi is normal because I'm doing these operations with phi 0, which was normal. This is a triviality. You have this continuity property for phi 0, okay? And it's a state because phi of 1 is 1. And I claim that it satisfies this for all x's in M, okay? This property. Well, first of all, note that you do have the property for x in P and P. How do you do that? Well, you do it first for x, a partial isometry. That's then trivial because it amounts to, you know, the properties here, right? So you, because of these properties, whenever you have projections that are equivalent, they, you know, you have the passage with 1 plus epsilon. You will have this trivially for x, a partial isometry under P, because of that, okay? And then, if x star x more generally has finite spectrum, okay, then it's just, it means that it's just the sum of such things, which all have, you know, mutually orthogonal this and that, and you just use the additivity, not even complete additivity, you know, and so it's completely trivial also, okay, so for phi 0, okay. So to deduce the inequality for phi itself, note that this property implies that for any x in M we have this. So here is the only real thing that, you know, where I'm using this definition. So to, you know, move it throughout. It's phi of x star x. Now x is arbitrary, it's in M. So I'm multiplying, I'm writing, I'm using the definition, okay? So this, I'm using that this is equal to 1 and the definition of phi, right? So this is 1. Okay, but this is equal to this, and now I change the summation from I, this was like first in I and then in J, and so it's equal, less than or equal by the first part with, you know, changing the the summation, so to say, and doing exactly the same calculation, which gives you 1 plus epsilon phi of x star x. Okay? So it's very simple. So now, if phi is a state on M that satisfies this, then I want to prove that it satisfies this. So, well, by complete additivity for all projections. So I'm only requiring this for projections. Of course, because this involves dim. Dim is only defined on projections so far. So by complete additivity, it's sufficient to prove it for projections in F. You remember, F was those projections which had dimension 1 over 2 to the n, for which we have with the V1, V2, V2n as in level 10, that, you know, phi of P is phi of Vj, Vj star is less than this for all j's, so that you have, this is just a, you know, plain silly calculations which shows very concretely that you have this inequality for P in F, for which, of course, here you will have 1 over 2 to the n. And, you know, it's just completely trivial. Now, with this at hand, we define, as I said before, tau on M as follows. First, for x in the unit ball of the positive cone of M, for which we take x in its decomposition this way. Okay, I define tau of x to be sum over n of 2 to the minus n dimension of En, which we have. So that's how we extend it to M plus, actually to the unit ball. Then by homotety, you just inflate, and of course you have a little problems of showing that it's well defined, but it's nothing really. And then on the self-adjoint part of M, this way, where x is equal to x plus minus x minus is the usual decomposition to positive and negative part. And finally, you complexify. Okay? Okay. And now, by lemma 11, by the last one, we have that for any epsilon there exists a normal state with this property, okay, for all projections, okay? You remember, this is what we showed. I mean, we put it differently, but it shows that the dimension minus phi is less than epsilon, okay? By the linearity, this will imply that on the unit ball of the positive, it's less than epsilon, and so for the real, you lose a 2 epsilon, and then for all x in the unit ball, 4 epsilon. And so for the addition, you have less than 8 epsilon. So that's it. It's over. You prove the linearity. So, of course, by definition, we have that, trace of ux, u star is equal to trace of x. For x's in M and unitaries in M, so tau is a trace state. Why you have that? Well, you have it for projections, and so for M plus, and so on, okay? So it goes on and on, right, for that property. Now, of course, from the above argument, it also follows that tau is a norm limit of normal states. You see how we approximate it with normal states, right? So which implies that tau is normal. That's an exercise, trivial exercise. So, well, I like this proof. I think it's extremely instructive. And notice that we basically, what we did, so I put it as here like that, but you can put it as, in this format. So we split it first in P1 and 1 minus P1, then this part we split it in 2, P2 and the rest, then this one in 2, this P3 and the rest, and so on. Each time, this picture also emphasizes the VNs in some sense, right? So, and you remember, this is, in a way, I mean, if you also keep track of those partial isometries, then this is like constructing a copy of those matrix units that give you the hyperfinite II1, okay? So, yeah, so let's not, let's keep that in mind. I'll get back to that. Let me just point out that you have this more general result. The proof is similar, but it's much more painful, of course, which shows the following. So finite for Neumann algebras are those that have satisfied this axiom, the finiteness axiom. So now I'm not requiring factoriality, okay? And for a Neumann algebra that's countably decomposable, by that we mean, you know, basically any interesting for Neumann algebras are countably decomposable. But by that we mean that any family of mutually orthogonal projection is at most countable, okay? And for that, you have the following equivalent. M satisfies the finiteness axiom, so what we call M is finite for Neumann algebra. Okay, any isometry is necessarily a unitary element, with the fact that M has a faithful normal trace state, or equivalently completely additive trace state. So you have this equivalence, okay? And moreover, if so, then there exists a unique normal faithful. This is interesting. I don't think we will need it in this week, but it's good for you to know. There exists what's called the central trace. That is a map from M to the center of M, which, remember, if you would have a factor, this would be the scalar, so it would be a state that satisfies, so it's linear positive, it's a projection on Zm, and it's Zm bimodular, so it pulls out, you know, Z1 x Z2, central trace of that is Z1, central trace of x times Z2, like that. Central trace of xy, central trace of yx, so it has the tratiality property, okay. So, and any trace state on M will actually be obtained from this central trace by just composing with the state on the center. Of course, if you take any state on the center and compose it with the central trace, you get a trace state because of this. Okay, well, any trace state on M is of this form. So because of the countable decomposability axiom, of course, you will have on the center states that are faithful and normal, completely additive, so you compose with the central trace and you get your traces, okay? And actually, you know, with Bldg's theorem tells you that you can recover that central trace is just the intersection of the convex non-closure of the convex hull. This is operator norm, which is a remarkable fact of this averaging, which we call, because of that, the Bldg averaging of x. Okay, so you move around x with add u, with the action of by add u of the unitary group of M, and that's it. Okay, so this is the more general theorem for not necessarily factors. Okay, and since I missed to prove this implication in the factorial case, let's do it in this generality because it's completely trivial. So if you have the finiteness, if you have the trace, okay, a faithful trace, and you have u star u equals 1 for some unit, for some element in M, then u minus u star, which you would like to be equal to 0, right? You want to prove that u star u equals 1 implies u star equals 1. And indeed, the trace of this is 1 minus the trace of that, but trace, you know, doesn't distinguish order, so it's u star u, which is 1, so it's 0. And so u star must be equal to 1 because of the faithfulness. Okay, so Now, let us move on. Well, I have introduced here, you know, after all we needed here was to have a trace. We could even take a star operator algebra M0 and B of H that's closed in operator norm, which is what we call a C-star algebra, which, by the way, by the Gelfand-Naimark-Siegel theorem, can be described abstractly as a Banach algebra with the star operation, or an operation like we said here, and which satisfies this axiom. The norm satisfies this axiom, which is what we call an operator. Or in other words, if you have such a, so of course any C-star algebra satisfies that, but conversely, if you have such a Banach algebra, that this says that, you know, you can represent it faithfully on a Hilbert space as an operator algebra non-closed. Okay, so here you have this abstract characterization, and I'd like to get something similar for our II1 factors. Now, if you have a unital C-star algebra and tau is a faithful trace on M0, so I'm only assuming now C-star algebra axiom, then you can define this norms. Actually, you know, it requires a bit of work to prove that it's a norm. It's easy for p equals 1 and p equals 2. And one denotes by LP of M0 the completion of M0 and this norm P. It's clear that you have this. This is easy. This is the more difficult is to show the norm property. I mean, the fact that the norm P of x plus y is less than norm P of x plus norm P of y. I leave you that as an exercise, which you may find, you know, challenging, but do it in B of H. After all, supposedly we have everything is in B of H, or even just for matrices. Okay, and which gives us these inclusions, of course, like in the function commutative case, function algebras. So we have, of course, L2 is the interesting thing, is actually also L1. That's the only ones actually we will use. That's a Hilbert space, of course, with respect to the scalar product given like, it's a Hilbert norm. The norm 2 is a Hilbert norm, and the corresponding scalar product is this. And this map, which of left multiplication by x on this L2 space, like we did before, is a star algebra isometric representation of M0 into B of L2, and you recover the trace as a state, as a vector state. Okay, it's isometric. That's because of the faithfulness. This is all exercise, and you also have the multiplication from the right row of x, okay, which is a representation of M0 op on L2, which the two of them commute, and okay. Yes, this is the more generally I'm saying here because of this isometric thing, right? The norm is, I guess, I hope I'm right here. And so you have these ways of, you know, these properties, which actually, you know, of course, this is for p equals 2 that I am claiming here that it's an isometric representation. Okay? And also the norm 1 is given like that. You can, it's the soup of this. You can recover it in this manner. Although you define it, you know, so it's, and this also shows that the trace extends to a function on all L1, and it's continuous. All these are exercises, but not that easy. So the reason I stated those actually was because I was keen on formulating this theorem, which is the abstract characterizations of finite von Neumann algebras. It's, you know, this was a big problem in the 50s. It's being said that Gelfand and Naimark were working on this problem when they found, you know, the axiomatization of C-star algebras and kind of how to say, cornered, the concept of this, what we call today C-star algebra, so the norm closure. They could axiomatize those operator algebras, the norm closed ones, but not the weakly closed ones, which is what Sakai proved later in 1960. When was Sakai's paper? So we celebrated 2 years ago, 60 or 50 years. I don't remember. It's 67 or 57. We cannot ask Masarinchi, we cannot hear. Anyway, so, and in a way this includes Sakai's theorem. So this is, so I'm taking a C-star algebra with a faithful trace test, but I'm using the notation M because we will axiomatize it as for Neumann algebras. So the following are equivalent. The image of lambda, okay, which we define, that left multiplication. Remember, this tau is a trace and it's faithful. Okay, this is a von Neumann algebra. So in other words, it's VO closed, or if you prefer, SO closed. Lambda is the commutant of rho of M. So the left multiplication by M is the commutant of the right multiplication. By the way, that's equivalent to doing the other way around. And now this is very interesting and kind of useful that the unit ball of M, this is completely intrinsic. So here are Hilbert spaces, but here is not. So here it's just a C-star algebra, and I'm requesting that the unit ball of M in the operator norm is complete in the norm too. Okay? So that's completely axiomatic. Okay? But also the fourth one, this is Sakai's, okay? This is Sakai's in a hidden way. And that's genuinely Sakai, which says that as a Banach space, okay, M has a predual. And actually, I'm saying exactly who the predual is. It's L.1 of M, with the duality given this way. Okay? And it's really, very much parallel to, proving this thing for L infinity with L1 and, being closed. What I was saying before, that, L infinity is, it's the function algebra of measurable stuff, whatever, and that's complete, the unit ball of which is complete in the norm too. Okay, and as in the construction of R, okay, actually also that, so if you just use what we've done there, it's basically, one can, with some effort, do all these things, as exercises. Okay, so what are the II1 factors? It's a terminology we have not used so far. It's an infinite dimensional finite factor. Okay, so it not being finite dimensional means simply that it's not n by n matrix factor. Okay. So that's what we call it. So any finite factor that's not n by n matrices, okay, is what we call a II1 factor. So R is a factor. You remember, I left it as an exercise, but it's an easy one. It did have a trace, okay. It's obviously infinite dimension, so that's a II1 factor, okay. So that's here is the reason we call it the hyperfinite II1 factor, okay. The word hyperfinite has a reason for that, and we come to that in my lecture tomorrow. The construction of the trace on a non-atomic finite factors, on a non-atomic factor satisfying the finiteness axiom, is based on splitting recursively one diagonally into equivalent projections with the underlying partial isomerity generating. You remember I emphasized, some notations when we constructed R, and those are exactly, it's exactly what I pictured here. So this is what the picture that corresponds to the Pn from our unit measures in an arbitrary II1 factor. Now all those, by the way, are II1 factors because they had no atoms and they were finite. Okay, they were not finite dimensional. This is what we were doing with the so-called unit measures. If you keep track also of the partial isometries that give you those equivalences, okay? So it's this picture, okay? But that we also emphasize in the construction of R uniquely determines a hyperfinite one factor. So this just shows, just the construction of the trace shows you that R embeds into any one factor, okay? So now, of course, the unique trace in a one factor is a dimension function on PM. We even called it dimension, okay? By that I mean it's a functional which satisfies that the dimension of P is equal to the dimension of Q if and only if the P and Q are equivalent. Also, actually, I should have said that tau of P is less than tau of Q if and only if P is majorized by Q. And the range is 0, 1, is the whole interval. So you have this fascinating phenomenon of so-called continuous dimension, okay? So you have, right? So if you would have some sort of geometry underlying these things, okay, then everything will be, with dimension, the indices, all that will be, continuously valued rather than just discretely, over the integer. Now, also a key thing is that any von Neumann subalgebra that you take, if you take the orthogonal projection of L2M onto what I should call L2 of B, but it's really, I view it here as a subspace of L2 of M. So it's the completion of B inside here, or the closure in the NOR 2 of B hat in here. Okay, so this orthogonal projection, I mean, it's here inside you have M and here inside you have B. Well, with the hats, but let's forget the hats, okay? So this is a completion of M, this is a completion of B. And this orthogonal projection is very easy to see that it's positive as, in terms of, if you take any element in here, actually in M, that's positive, it goes into a positive operator there, okay? So that tells you right away that it will take M into B. So therefore, it will be a projection of M onto B, which is positive, and that, of course, for instance, by Tomiyama's theorem, one knows that it's automatically a conditional expectation. Now, by its very definition, you see that it satisfies, that it preserves the trace. So what I'm saying is that this orthogonal projection restricted to M, okay, but if you want, you should put the hats, but after removing the hats and just viewing it as an application from M into B, then I change the notation, I call it capital EB. It's a conditional expectation that preserves the trace, and it's unique with this property. That's very important. We have conditional expectation like for n infinity on sub-sigma algebras. So this is perhaps my last slide for today. I'm using, I will define what's the amplification of a II1 factor by a positive real number. So first of all, notice that if you have for any n, well, also for n equals 1, but that's not interesting, I can take n by n matrices over M over a II1 factor. So M is a II1 factor, we forgot to say, but actually it's a continuation of this. So M is a II1 factor, okay? I'm taking n by n matrices over it, or if you prefer this kind of tensor product. It's a II1 factor, and it has a trace state. If you want the tensor product between the normalized trace here with the trace here, or if you prefer this. So since we always denote by tau the trace here I'm talking about the trace on M, but here is the trace on this new algebra, and that's the definition. You sum up the elements of the diagonal of this matrix as xij, and you divide by n, of course. Okay, so to take it to be a state. And since it's a trace state, and this is well, any of those axioms, any of those equivalent properties would immediately imply that this is a II1 factor. Okay, also these corners of M are also II1 factors with this trace. I'm renormalizing by multiplying with this scalar. And obviously the isomorphism class of this only depends on the trace of P. And now, with these two, let's notice that actually you can this is an amplification by n, and say if T is the trace of P, this is the amplification of M by T. This isomorphism class of this PMP is like an, T by T matrices over M, where T is the trace of P. Now let's do that put these two together and do it for any number, positive number, real positive number. So you take first an n, an integer larger than it, and then a projection in here that has trace equal to T over n, which is now less than 1. And the isomorphism class of this is what we call M to the power T. And this, we call it amplification of M by T. Now you show very easily that we made choices here, right? For the n, you can take a bigger n, which will force a projection of different trace, so that you have still this. And you will see immediately, this is the exercise, that it doesn't count. Okay, it doesn't matter. How do you do that? Because you will put, if you take M larger than n, you put the n by n matrices as a corner of the m by n. So this is m by n matrices, and this is n by n matrices. Okay, and when you cut and do all these things, you see immediately that it's okay. So did I do it properly? I hope so. So you have this formula that m to the m to the s to the t is m like to the power s times t. So this will you have this obvious formula. By the way, m to the s, attention, so unless you take s to be an t or s to be an integer, this is non-canonical. It gives you an isomorphism class, but nevertheless we view it as a II1 factor, okay? But it's an isomorphism class, okay? And one denotes by f of m the set of t's with the property that m to the t is isomorphic to m, and that's clearly a multiplicative subgroup of R plus because of this, and it's what one calls a fundamental group of M. It is clearly an isomorphism invariant of M, okay? And I guess we stop here. I'll do this next time because it's already 5 o'clock, and so we'll define next time, we'll classify all, you see there is this problem. We characterized abstractly the II1 factors, but we did not clarify what are all possible von Neumann representations of a II1 factor. Okay, it can be represented in various Hilbert spaces as a VO closed algebra, and we'll see at the beginning of tomorrow's first hour. This is what we will begin with, classifying all this representation, which we will view in fact as Hilbert modules over M, left modules, of course. I mean, you can view any representation of a group or of an algebra as a module, as a Hilbert module. And we'll show that actually there is a a natural dimension function for that of the Hilbert space over this, of the Hilbert M module dimension over M, and which takes any value between 0 and infinity, and with ordinals, cardinals after that, and this is, it classifies completely that number. Okay, so I stop here for today.